So we have replaced the original PB7200 with a later model unit, a PB7220. The primary difference being that there's newer electronics. The electronics have been significantly upgraded such that we can have a second channel if that's desired. More importantly to what we're talking about with the interferometric effects, this unit is different in that it now has the ability to operate a phase modulator. So here you can see we have the two lasers as before, the main motherboard with the electronics, spot for a battery, but the big difference is this optical circuit here with a phase modulator. This has replaced the simple 2x2 splitter, and the phase modulator is controlled by the lock-in amplifier on the board. Again, the fiber circuit splits the power to the terahertz head and the terahertz detector. Now let me put this back together and we'll take some data and show you how this works. Now you will have noticed that the heads are a little closer together in this case, and that's because the fiber lengths inside the instrument are a little bit shorter in difference. What I need is to replace this fiber with something a little bit longer so I get a greater working distance, but I don't have anything in the shop right now. So we have now fired up the software for the PB7220. This is the instrument with that measures the first and second harmonic of phase modulation on the detector. And so what we'll do is we'll first go to the dwell screen, the dwell tab, which is over here, and we will put it to 800 gigahertz, so we're not near a water line. And we're going to tell it to just go to that frequency and stay there. And what you have here is, this is channel 1, this is the first harmonic, and channel 2 is actually the second harmonic. And what you'll notice as this thing stabilizes is that in regimes where the first harmonic is a peak, the second harmonic is a null. And over here you have the two swapping positions as well. So as this stabilizes, you'll reach some equilibrium. Stop seeing this occur. And any phase noise here in the first harmonic should be countered by the opposite phase noise in the second harmonic. Alright, so we're going to stop the dwell. Instead we're going to go to a scan now. And we are going to scan from 750 to 900 gigahertz with a 1 gigahertz step size resolution. We'll just do a single scan up. And the point I want to make with this instrument is this is the first harmonic and the second harmonic here. Unfortunately, these lasers that are used in this instrument can tune from 750 gigahertz up to 1.5 terahertz, so we can't use the lactose sample like we did previously. We're going to skip taking a background and instead just look at the transmission of air in this frequency range. So I can switch to raw power, and what you'll notice is where there's a peak, there's a null. And that means we're not losing any information or absorption data when the first harmonic is at a null because we find it on the second harmonic.
and vice versa. All right, now